Good evening, everyone. Welcome to week 7 problem solving session for the course Probability for Computer Science. Okay, and my name is Bhavya. I'm a PhD scholar at IITM. We are keeping these problem solving sessions at Tuesdays, 6 p.m. to 8 p.m. Okay, so this is an 8-week course, by the way. So this will be the second last session. So the last session will be happening on the next Tuesday. Okay, good. Uh, Now that we have that announced, any other announcement? I don't think so. So yeah, let's get on to solving some problems. So last week, what did we do? We did Markov chains, more on Markov chains. Okay. Last week we did Markov chains, and we did sampling. Some simple questions on random sampling. Mm. Okay, but we could not fully uh, solve questions on random sampling. I remember, so a lot of questions were missed out. So this week, I mean, even though this week's content is more about the probabilistic approach, okay, we'll also do some questions in sampling first. Okay, then we'll move on to probabilistic approach. So probabilistic approach has things like hashing, okay, and max cut, randomized max cut algorithm, and what else is there? Some subset, not subset sum. Okay, for now let me call it subset sum.
Subset free, I guess. And then the other one was
Yes,
the
some free
Remsen.
subset, right? Some free subset. Okay.
Remsen numbers.
And Ramsey numbers. Okay, and so we'll be solving some. Thanks. Yeah. We'll be solving some questions which are some additional applications of the probabilistic approach, because most of these you can already see it in the lectures. For example, hashing and Ramsey numbers. Hashing also, I'm giving one question just for completeness. Ramsey numbers, I wanted to come up with a question with that, but yeah, I couldn't get a suitable question. Okay. Regardless, uh, we'll first solve a few questions on sampling. Okay. So, what is sampling? Okay, I think we talked about it. Like, it's, you know, picking objects from a set, okay, um, following some probability distribution. Okay. For example, like, say you have some products coming from the factory, okay, and you need to check whether like the products are defective or not. But the products in factory, check if defective or not. Like what percentage is defective. So one strategy would be you manually go through each item, okay, in the factory and check if they are defective or not. But it requires more effort. But it requires more effort and more time and any other resource. The so what is an alternate? So this is not what they do in the factory, right? At least I mean, most factories, they do not possess the capital to actually go across each product and test them, okay, and check whether they are defective or not. What they rather do is they'll take samples, right? So what would and what okay, so an alternative is that they'll sample the items. Now, one way to sample would be, say I sample first 10, or I sample um, last 10, okay, or I sample even items, and so on. But I mean, what is the problem with this approach? I mean, it may happen with, because every time I'm sampling the first 10, maybe it so happens that my machine exactly always produces, say, good items for the first half of items. So in day one, I do this, okay, I do the sampling run, and in day one, I check the first 10. Since the first 100 products are always, non-defective by the factory, right? So definitely I'll sample the first 10 and I'll say, oh, it's so good. And so every day I'll check and it'll always be same, right? My strategy is always same. And let's say I did this strategy, sample the last, okay, sample the last 10 numbers, items. So what do? If this was the case, let's say my factory, due to some situation with the machine, the last 50 items or the last 100 items, okay, are always non-defective. Then every day I sample the last 10 items, I'll say, oh, good to go. But maybe the first set of items, first half of items are actually defective. There are so many defective items there. And I sample even items and so on. Okay. Now, those kind of issues persist, right? So, this is a very bad kind of sampling. This is a deterministic sampling. And I hope, yeah, you can understand why this is bad. What would you rather do? You would randomly sample, right? You would pick them in no particular predictable order, right? So maybe you toss a coin or roll a die. Okay, that's even better. But you basically take some random choices and then pick them up and then try it off. You want to break the symmetry so that no particular pattern exists. First day I sample randomly, second day I sample randomly, third day I sample randomly. It is very unlikely that I don't break the symmetry. That is, I always sample with respect to a given pattern. It's very unlikely that I do that, right? So that is the advantage of sampling, and this is not just about factory sampling, item sampling, and all. It's used everywhere in computer science. It's used everywhere in theory as well as practice. Okay, and so this is an introduction to sampling. Now, okay, we come to the science of sampling. Okay, the first two questions are based on that. Now, these are some very interesting questions. Okay, try to solve them. Okay, this may have been done at the lectures also, but I just want to touch upon it because this is but very helpful. Okay, so here is the idea. Okay, suppose I have to sample one element from the set 0 to m minus 1. Okay, and I want to do so uniformly at random. However, to make my choice, I have only an unbiased coin to help me. Explain how the sampling can be achieved. Okay, so if you notice, randomized algorithms, okay, we are always talking about tossing coins, because tossing coins is easy to visualize in binary. We won't talk about rolling a die or picking from a set and so on. I mean, it's more common to see that you are tossing coins in randomized algorithms. Okay, now why? There should be something about tossing coins that makes it so general, right? It so happens that you can use tossing coins to simulate picking items from a set also. Okay, so here is a set 0, 1, 2, 3, and so on till m minus 1. So this is the set of items. Okay, and what is the size of the set? M. What you want to do is you want to sample one element uniformly at random. But how do I do that? The only access to randomness I get is via a coin, an unbiased coin. That's all I have, which I'm allowed to toss several times. Okay, allowed to toss more than once. Okay, so what I want to do, I want the probabilities to be uniformly at random. What does uniformly at random mean? What should the probabilities be of picking each element? Say, what is the probability of picking 0, say, or 1, or, okay, let's say picking uh, 5 from S?
1 by m.
1 by,
Uh,
1 by?
so, but then since we are picking the elements with the help of a coin.
Hmm.
So, say if the coin results into the head, then I will pick the element. Otherwise, I will leave the element.
Okay, so
So now,
okay.
so now in this case, if I am picking 5 with the help of the coin,
Hmm.
then that would be half 1/2.
But
And
yeah,
but if it is uniform at random, that would be 1/m.
it should be 1 by m, no? It is supposed to be 1 by m. I'm going, yeah, I was about to get to that point. Okay, but why is it 1 by m?
So we have m possibilities, and every pick is equally likely to happen.
Equally
So
likely,
that is
exactly. Yes, good. So uniform distribution means equally likely. So picking 5 is equivalent to, is the same probability as picking 1, which is same as probability of picking 2, right? And so on, which is same as probability of picking m minus 1. Oh, maybe this should be 0 and this should, okay. Picking 0 is same as picking 1 is same as picking 2, and which is, and so on. Yeah, Harsh, just give me 1 minute, okay? And all of these are non-zeros, okay? So, and their total probability is 1, okay? So it can only mean that, so their total probability is 1, which means that, summation over probability picking I, element I, is equal to 1, right? I equals 1 to m, right? 0 to m minus 1, right? And so if I uh, see it as each of them are same, so I might as well multiply this with m minus 1 times any guy. So probability of picking any arbitrary person, because they are all same. So picking, say, 1, right? Because the probabilities are all same, is equal to 1. It's not m minus 1, sorry. There are m elements, 0 to m, right? So, so probability of picking 1 is 1 by m. And so on for 2, 3, 4, and so on. So this is uniform distribution. Right? Okay, Harsh, yeah, tell me.
So I was saying that basically in this problem, according to the result the coin gave, either it's one or zero, irrespective of heads and tails. So according to that, we are supposed to pick out an element from the set. Am I correct?
Yes, yes,
But
yes.
how does that work? I didn't understand the mechanism entire.
Yeah, I've not explained the
Okay.
mechanism yet. Okay, that I've left as a mystery
Okay.
till now. But you can think of ideas to
Okay.
do it. I'll give you for a
But but
moment to
but,
think about it.
but what I
But
said, it's essentially correct, right? That's the whole idea, na? Okay. Yes.
yes,
Okay. Thank you.
yes, yes. Okay, yeah. And so one strategy that Goel was proposing was this, right? Well, that you are pick. Oh wait, um, what did you say exactly? Oh yeah, yeah. Okay. Oh, that you are just picking one element. Can you repeat your
So
strategy
what I
again?
understood was that I have to pick just one element. So then I said that I will flip
Yes,
a coin. If it is head, I will pick the
yes.
element. Otherwise, I will leave the
Uh,
element. So basically, I picked one element from the set. Now, if I have to,
yes.
so similarly, I can keep on picking other elements, right? And in that sense, yeah. So a sample will get prepared, and I'll keep on. So like say, if I want to prepare a sample of the size say k, then
Uh,
it shows that the probability of getting selected was half for every element, and the probability of getting that kind of the subset having the k number of the elements would be 1 by 2 raised to the power k.
yes, but there is a slight detail here that you are supposed to pick only one element, right? But the first toss decides for which element. First toss decides for, say, the first element, right?
Yes, yes, right.
And the second toss decides for the
No,
second
this
element.
is not necessary. Say if I have to pick only one element, and if I am confirmed that I am going to pick the element number 5 only, so then I'll flip the
Okay.
coin only once, and the probability would be half.
Yes, but you need to do it in some order, no? Because I just have one coin.
So how many elements are required to be selected?
There are m elements. So take for example m equals 100.
Yes.
Okay. So there are 100 elements. Now you'll need to toss the coin, right? So what I mean to say is, let's say what is the event when you pick say 5 from the set according to your strategy? I think that would be the fifth coin toss, right? According to you.
No, not the in that sense,
Okay.
yeah. Because I thought that I am already knowing this thing that I have to pick the element. That is not.
Oh, no. Otherwise, it won't
Yes,
be
yes.
random.
So yeah, so
Yes.
in that case, yeah. That,
So there the issue becomes, not only is it not uniform, it becomes dependent
yes,
distribution. That like the second picking the second element depends on the fact that the first element did not come to heads.
yes.
And picking the third element depends on that the second and the first element did not come to heads. So the probabilities for the upcoming elements keep decreasing.
Then I need to think. I mean, ponder up. Yeah.
Yes. Yeah, that's okay. It's not immediate. Okay, but okay. The strategy one is toss ith time. Okay, toss uh, ith toss is heads. Then pick element I. The problem is, what is the problem? It is not uniform and not independent. Okay. Any other strategies?
Sir,
If
Over
not,
here, you told it's not uniform and not independent. How is that?
yes. So not uniform. I hope this is clear, or should I explain not uniform also?
Just
Okay. Yeah, I'll explain, no problem. So the strategy is that if first toss, so it becomes a decision tree basically. Okay. If first toss is heads, okay, then if yes, if no, if yes, then pick element one. Okay. Now if no, then what do? You do a second toss. Okay. If the second toss is heads, yes, then pick element two. If no, then you keep tossing. Third toss is heads. Is the strategy clear? Or should
yes, sir, I'm able to part.
strategy at least, not the probability?
This part, yes. First toss is heads. Yes. No, that part.
Okay. So and I keep doing this. So basically, ith toss stands for picking ith element in the set. I'm supposed to pick only one element, okay? And the probability of picking that element should be 1 by m. I should it should be uniform. I should treat all the m elements equally, right? This I am alleging that this is not uniform. Okay? Why? Okay, let's look at the first element. What is the probability that I pick element 1? Okay,
Point. um,
pick element 1 is just a toss of coin. Yeah,
It's a
Vishal.
0.5 probability.
Yes, 0.5 probability. Because it's just the probability of getting heads, right? That's all.
Yes, sir.
Good. So, what is the probability of picking element 2?
So it's the same 0.5, 1 by 2.
No. Now it's not.
Um,
Because uh, picking element 2 is depending on getting a heads in the second toss while you did not get a heads in the first toss.
okay,
Is it not?
yes.
Yes, right? Okay. So, the probability of element 2 is that second toss is shown is heads, given that first toss is tails, and they are independent events, so I can multiply them. Probability that again second toss is heads times probability that first toss is tails. Okay, which is 1 by 2 times 1 by 2. Right? Okay. Yeah, so 1 by 4. Virtual camera. Yeah, I don't mind if the camera is on. That's totally fine. Okay. And so uh, where was I? Okay, yeah. So you get it, right? So already there is a disparity. Now, what if can you predict what should be picking element 3? Can you predict?
Sir, that
1
was
by 8.
problem. Actually, see, over here we found that probability of element 2
Good,
it's
Abhishek.
independent of
Yes.
the first one, and also it's uniform. But
Yes. But you see that this strategy 1 is not uniform, no? Because what you are getting is the probability of picking element I is 1 by 2 to the power I. So probability of picking element 1 is 1 by 2. Probability of picking element 2 is 1 by 4. Probability of picking element 3 is 1 by 8, and so on.
oh,
This is not how a nicely behaved
oh,
uniform distribution works. Uniform distribution should treat all the elements equally.
Okay, now that you explained, I see why it's not uniform. 1 by 2, 1 by 4, 1 by 8.
Yes,
Okay.
yes, 1 by 2 power m for the m. Yeah, that's right.
Sir, I have a question.
Okay.
Can I? Yes, sir.
Yes, Avisha.
Sir, you said that if on the first point, if we get tails, then we will be moving on the second point or second object. What if on the
Yes.
first point we got heads and we picked that element, then won't we moving to the second point anyways? Like,
No, we won't move to the second toss because we are only tasked with sampling one
oh,
element.
okay, okay. Yeah.
Okay, so we are supposed to sample only one element. So it's like it's like when you throw a die.
Yes.
Okay, when you throw a die, what is the probability of getting a 3?
1 by 6.
And what is the probability of getting, say,
1
5?
by 6. Yes.
It's the same, right? It should treat it all equally, and I'm throwing the die only
Okay.
once. So you can imagine this to be simulating a throw of a die using
Yes, I
coin tosses only.
yeah.
You get it? So you are only simulating one throw of the die. So you can think of it that
Okay,
way.
okay. I'm sorry. Actually,
Okay.
when I focused on the strategy, I forgot the question that we were supposed to only do it once.
Oh no. That's totally fine. No
Then
need to apologize. Yeah. Okay. Sure. Okay. Yeah. Harshul, is it clear?
Yes, sir. The not uniform part is clear, and not independent
Sure.
part.
Not independent part is clear. Why? Because it would be clear. Why? Because stare at this. Probability of picking element 2 is probability of second toss times the probability of first toss. First toss is tails. So this element is a complement of this element. No, so this probability is the complement of this probability. No, first toss is tails is same as first toss is complement of first toss is heads. So you see that probability of picking element 2 depends on the fact that the second toss is not a head. The first toss is not a head. That's why we explored this branch at all. Otherwise, we would not have even have landed at this branch. So this depends crucially on the fact that the first toss is not a heads. That's why we landed here. So these probabilities are interconnected. They are cascading. So second toss depends on the first toss, third toss depends on the second toss, and fourth toss depends on the third toss, and so on. That the every ith toss depends on the I minus 1 toss has failed and has led to a tails or something. Okay, so hence it's not independent. Okay, but this is just an extra thing that I said. What we are more focused on is uniform. Anyway, if it is uniform, it means that it's independent. Okay, so you just analyzing uniformity is enough. Okay, is that clear, Harshul?
Yes, sir.
Okay, great. So now let's look for another strategy. Okay, so I want to give a hint here. Okay, so it looks like you can't decide whether to pick an element or not using a single toss. No? An alternate idea would be toss several times, say k times. Okay, k, I don't know what k is, you tell me. Okay, alternate idea is toss k times, then make decision. Okay, toss k times, then make decision. Okay, let's see if you figure this out. Toss k times, then make decision. So what does it mean? When I toss k times, what do I get? Tossing k times. Okay, tossing k times. What do I get? I get something like heads, tails, heads, tails, tails, heads, and so on. No? K outcomes. Right? And I'll look at this, I'll say, oh, it's heads, tails, tails. Okay. Then that means 5 or something like that. Okay, then I make my decision. Okay. So what does it look like? So here is the mapping. Okay, here's the mapping. Heads, 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 heads. Then I'll pick 0. Okay, these are k length. Okay, because k many tosses. This is the outcome of it. In case I had tossed k times and got heads, 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 tails, heads, tails, and then what will I do? I'll pick 1. And again, now I'll do heads, 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 and so on. Heads, tail heads. Then what did I do? Pick 2. And so on. And here, if I finally all tails, then I'll pick m minus 1. This is the mapping. So can you most of you are CS students, so can you see some?
So 2 raised to the
Something
power
here.
k here is equal to m, and therefore the value of k would be equals to log m. So because I need to map 2 raised to the power k number of the possibilities to the m number of the possibilities.
Yes, it's a
Projection,
bijection.
yeah. So then,
And further, can I associate with some type of
yeah. So that
encoding?
encoding could be, that encoding
Standard
could be, like say, the number of the tails. Let us pick. Say the number of the tails is equal to 0. So, and the number of the tails is equal to. So I mean, what would that be? So 2 raised
Sir,
to
may
the.
I answer? Sir,
Yeah.
it can be associated to one hot encoding in which each index which is on, like each index which is 1 is associated with a specific output. Like if there are all zeros, so it will be first, if first bit is 1, then another element will be associated with that. If the second is 1, like that.
Okay. Yeah. One hot encoding would
Yes,
also
sir.
work. I agree. Now, okay. One hot encoding. The issue with one hot encoding is that what if my tosses don't lead to a one hot? Okay. For example, like what if for example, this itself, this is not a good one hot encoding, no? Like there is like heads, tails. I mean 0, 1, 0, 1, 1, 0, 1.
Huh.
So one hot insists that there is only one. So there is an encoding that is actually simpler than one.
So that
I
would
mean,
be, let's say,
like what is the first
so
encoding that you learned?
so it could be like, say, I focus on the tail outcome, and then 2 raised to the power the position of the tail. Like, yeah.
So
So
what is
like
that
say
point?
in the first case there is no tail, right? So let us map to 0, and for all t's let us map to say m minus 1, and then for the remaining thing, like say if I am having only t at the end, so t is at the position 1. So therefore it is going to be mapped to what? 2 raised to the power 0.
Yes.
So let us map to the similar to the one hot encoding, but then
but there is a
there could be more than
what is
yeah,
this?
more than there could be many t's. So then
Okay.
so we can compute the binary equivalent of decimal equivalent of this thing, right?
Yes.
Convert this h into a 1 or t
Yes.
into a 0, and then get its binary decimal equivalent and map it there.
Yes. See, if you Good. So if you take all the heads as 0 and all the tails as 1, this is nothing but binary, no? So this is nothing but 0 1 0 1 1 0,
Yeah.
right? And any head tail configuration, k tosses can be encoded as a binary string, and every binary string represents a number, right? And if I want to represent a number from 0 to m minus 1, then how many bits do I require? I need log m bits, no? So this is nothing but binary. Yeah, Harsh, wait, who raised the hand? Show one, no?
Yes, sir.
Yes, show one.
Sir, we don't know how many balls are there. If there is like 128 balls, let's say, so we can number the balls from 0, 1, 2, 3 to 127. And if we, so we have to just toss 7 times. If we toss 7 times, we will get the combination from 0 to 2 to the power 7, which is 0 to 128, or 0 to 127. And if we replace head with 0 and tails with 1, we always get a unique number, and we always get a number actually. And what number we will get, we will pick that one. That's how it is uniform.
Yes. Exactly. So, for example, like if your if your set was 0, 1, 2, 3, 4, then the set of possibilities are heads. So what is k? K equals log 4. Okay, log 3. Okay, log 3, which is 2. So 2 bits are enough to represent it. So you can get heads, tails, tail heads, heads. Again, like this is nothing but 0, 0, 0, 1, 1, 0, 1, 1. I mean, on tossing 2 coins, that's what you do. No? And then you make your decision. If you had got 0, 0, what is the binary equivalent of 0, 0, 0? If you had got 0, 1, what is the binary, decimal equivalent? Sorry, not binary, decimal equivalent of 0, 1, 1. If you had got 1, 0, then you write 2. And if you had 1, 1, you write 3. Okay.
And sir, here each toss is independent from their previous outcome. So it's already independent. And by that way, the chance of getting every ball to be picked up is always there. So in that way, we can solve this problem.
Yes. I'll come to that. Yes, good. Okay. So this strategy is clear. So I toss log m many coins. So what is the final strategy? So this is k is log m many coins, and make decision. What is the decision? Decision is pick the decimal equivalent of that string. Let me call that string str. Toss k many times and get str, which is nothing but the configuration. Okay. And do the decimal equivalent. Is that clear? Everyone, strategy is clear?
Yes, sir.
Okay. Harshul. Okay. Harshul. Okay,
Yes.
Ankita. Good. Okay, good. So now we'll analyze the probability using this. Okay. So what is the probability that any element I is picked? Okay. For any I. Okay. Our target is 1 by m. Remember that. Okay. I is picked. Now that will be the fact that I got okay, there is only one configuration, okay, that will achieve this. Okay, and by the way, how many configurations are here? 2 to the log m, right? Probability that I is picked is 1 by 2 to the log m, which is 1 by m, give or take. It's the closest you can get to 1 by m using just tossing, right? Because of this, because m need not be a power of 2. That's why. But so in case you don't know this fact, 2 to the log anything, okay, base 2 is that number itself. Okay. Okay, good. Right. So there you have it. So you went from um, uh, tossing coins to sampling elements uniformly at random. What does that mean? You can simulate throwing a die using by tossing coins. It's pretty interesting, right? So if you tossing coins is that powerful. Like the access to this randomness, half randomness, okay, access to this uniform distribution over heads and tails is enough to simulate any kind of enough to simulate, say 1 by 6 die a die through this distribution. Accessing this distribution is as good as accessing this distribution and any other uniform distribution. Okay. Now this is already very interesting. Okay, how to get from one distribution to another. This could be used to design an algorithm for random image picking in your phones. The photos are changed to zeros and ones, and then a number obtained is the index of the photo. Yes, yes. If you want to treat all the images equally, say, then this algorithm can be designed. I mean, this method can be used. Okay, and this is actually used also. I mean, um, uh, because there are a lot of problems. Okay, a lot of cases where you need to pick uniformly at random across numbers and all, right? But the computer works over bits, no? So how does it perform that? It does exactly this. It tosses log m coins and then picks from that and changes the distribution. Yes, good. Okay. Now, is it used in AI? I'm sure I'm sure it's used. Under the covers, definitely it's used. Under the covers, yes. Because okay, just give me one moment. Sorry, just give me one moment. Right. Um, okay, now comes the most interesting question. Part of the question. Just give me one moment. Sure. Okay. Oh yeah, sure, no problem. But you have a booking, no? Okay, sure. Yeah, just give me a moment. Yeah. Yeah, sorry, I had to change rooms. Um, to share my screen again. Okay. Uh, yeah. So, okay, what is the question? Is it used in AI? Yeah, yeah, definitely. I mean, randomization is definitely used, and if you want to use randomization where you are working over a non-binary distribution, then you definitely use this method because it's the simplest method. Also, it's a very efficient method. You just the time complexity is just log n, right? Okay, now comes a more interesting question, even more interesting question. Okay, so we saw that you can do, like, you can simulate die using a fair coin, no? So now here's the question, okay? Can you simulate a biased coin using a fair coin? Okay. Okay. Can you simulate a biased coin using a fair coin? Okay. So what is the bias? Well, it is alpha by m. So what you have, what we have is unbiased coin. Let me call that coin C, and the probability of getting heads is half, and probability of getting tails is half, right? Uniform distribution. Now what we want to is the opposite. We want an unbiased coin. Yeah, we want a biased coin. Okay, that the probability of heads can be not half but something else, some alpha by a by m. Let me call it. Why use alpha? And a and m are in natural numbers. And of course, probability of tails will therefore become 1 minus a by m. Okay. Now, this is what we want to simulate, biased coin. So that's what the question is asking. Alice and Bob play a game that involves a biased coin. The biased coin requires that the probability of heads is a by m. However, all we have access to is an unbiased coin. Can you simulate a single toss of this biased coin that says heads with probability a by m using unbiased coin tosses? I hope the question is clear. The question is clear, no? Go ahead.
Yes, question is clear. Yeah, question is very much clear. So I was thinking that, by the way, there has to be some relation between A and M so that this value still remains a fraction only and does not cause this one thing, the value of 1. So the value of A should be less than M, by the way. This
Yeah,
this
right.
condition
Sorry.
should hold true. And so I was thinking that why don't we flip this coin multiple times so that some of the tails, because then I will convert some of the, then I will reverse some of the outcomes so that everything does not remain in the, I mean, changes from half. So I was thinking that how can this be done? Yeah. Question is clear. Question is clear.
Okay, I'll give you a hint.
Yeah. What is that?
Remember the previous question? We were tossing log m coins,
S-
right? So can we think of a
So
simpler
like
strategy? So the usefulness of tossing log m coins was that each of these head tails head string, okay, that we get, log m length string that we get, represents a number. Okay.
What I am thinking is
Yeah.
toss log m coins, and whatever number you get, if that number is less than alpha, if the number is between less one what value is zero between zero and alpha, then you say it is heads, or if it is other, sorry, it is tails. If it is otherwise, it is heads. That's what we were thinking.
Nice. Yes. Yes. Yeah.
Thank you.
Thank you, Ashwin. Yes, that is exactly the strategy that we are going to follow. That is, we toss log m coins. I'll explain why this works. Okay. We toss log m coins and look at the decimal equivalent of that. Okay. Log m coins, and you get again the string str. And you get string str is some head, tails, heads, tails, heads, and so on. I mean, this is same as 0 1 0 0 1 0. Okay. Now, what you want to do is you make sure that x is equal to the decimal equivalent of this string, and we know it uniquely represents a decimal equivalent string. And the third part is check if x is less than a. Okay, check if x is less than a. If yes, output heads, otherwise output tails. Now, why does this work? Okay, we'll go back to this diagram. Okay, let me copy this. So look at this diagram. We are tossing k equals log m many times. You get these head tails patterns, which are nothing but zeros and ones, and you are getting these equivalents. Okay, now totally there are m outcomes, out of which if you cut off at the first alpha outcomes, just look at the first alpha outcomes. Okay, and then look at the binary number representing alpha. If your um, outcome represents anywhere from 0 to alpha, then you are done, right? Okay, in this case alpha minus 1, because you're starting from 0. Okay, and then next you have alpha. Okay, now it's just now you toss log m coins, and there are m many outcomes. Okay, close to m many outcomes, and what you do is you check if the decimal equivalent, which is this zone, okay, is within the first alpha many places, which is nothing but checking whether the decimal equivalent is strictly less than alpha. Right? Now, what is the probability of that happening? So, what does that mean? So then I'll output heads. So, what is the probability that my new coin, okay? So this is my coin C prime, is C prime. This original coin was C. Okay, toss log n C coins. Okay, this is my new coin C prime. Okay, probability that C prime outputs heads is nothing but the probability that the decimal equivalent, okay, of STR is less than alpha, right? And what is this probability over STR sampled over uh, 0 1 to the log n? Okay, uniformly at random. But what is this? What is the probability of this happening? Well, totally there are m numbers, out of which 0 to alpha minus 1 is alpha many. So the probability that C prime output set is alpha. And for the probability that output tails is of course 1 minus alpha. So good. This is the strategy. Is this strategy clear?
Yes, it is clear.
Okay, good. Okay, good, well. Okay. Shovan, Harsh, Harshul. Okay.
Sir,
Yeah.
just
Harshul.
could you explain this once more? I didn't
Sorry, can you
No, I
speak
mean
louder?
the last part I wasn't able to follow. Could you?
Okay. So but the question is clear. So I want to come up with a biased coin C prime such that the probability of saying heads is A by M. Okay. But all I have access to is a coin C which is unbiased. Okay. So take note, in the previous question, we were able to pick an element from 1 to m uniformly at random by tossing log m coins. All I'm saying now is that now that we have expanded it into a set, okay, of size m, and m is our denominator for the probability, I want to achieve this probability a by m somehow. So what I want to do is I want my favorable outcomes to exactly land in some area of size a. Okay, and how I do that is I toss log m coins and I get this string, binary string, right? And remember that each of these binary string uniquely represent an element in decimal from 0 to m, right? This is what we saw in the first question. Now what we do is, let's say x is the decimal equivalent, right? X is somewhere here, let's say. We check if x is less than a. Okay, I've written alpha here. Okay. A minus 1, a. Okay, yeah, very sorry. Okay, now if x is less than a, then output heads, otherwise output tails. Now this is the zone where I'll output heads simply. How many elements are here? A elements, right? 0 to a minus 1. And how many elements in total? M elements. No? That's why I'm getting a by m. So the probability that this new coin C prime outputs heads is the probability that the decimal equivalent of each of these coins, which are like 2 to the log m many coins, which is nothing but close to m, okay, is less than a. The decimal equivalent is less than a. Which one are favorable? 0, 1, 2, 3, everything till a minus 1. They are all good for me because these are the decimal equivalent, decimal values, which are strictly less than a. So a many out of m many satisfies. Okay.
Yes, sir.
Okay, good. So now comes in. Okay, Harsh, is there a, yeah? Harsh, is there a question? You gave a thumbs down. Okay. Harsh. So, is the question is clear, right, Harsh? You want me to explain the question also? Okay, question is clear. Okay. Now, um, the algorithm is simple. Okay, I'll just do it in a direct fashion. Okay, by explaining the algorithm first. The algorithm is simple that I'll toss log m many coins. What is m here? M is the denominator. Okay, log m many coins. I'll toss, and I'll get this log m length string: heads, tails, head, tails, and so on. But what we did was we thought of these heads as zeros and tails as ones. Okay, heads as zeros and tails as ones, and so it represents a binary number. So a log m length binary number can be converted into a decimal number from 0 to m minus 1, or m. Okay. And so what I want to do is I want to force the following behavior. Okay, I want a probability of a by m. Okay, I want to simulate that probability. Okay, of a by m finally. So already there are m elements here in the right. Somehow I want to say that my favorable outcomes is of size a. That way, favorable outcome divided by total number of outcomes, which is m, is the probability that I finally want. But the most simplest way to do it, there are other ways to do it. Definitely, you can take, the last a items, or you can take, let's say, the even a items, or the odd a items, or the middle a items, and so on. That's totally fine. But this one of the simpler ways to do it is simply check the decimal equivalent, check if it is less than a. If it is less than a, then it lies between 0 to a minus 1. And I mean, there are only a many elements, such elements, so therefore the probability is a by m. And in those, if x was less than a, then you were outputting heads, no? So the probability of outputting heads is exactly equal to the event that the decimal equivalent is less than a, whose probability is a by m. Therefore, the probability that you C prime outputs heads is a by m, and therefore tails equivalently, since it's saying no in all other cases, it's 1 minus. Okay, that's clear, right, Harsh? Okay, good. Okay, so here's a slightly challenging question. Okay, now, but it's even more interesting. So the bonus question being that, can they do the opposite? Can you simulate unbiased coin using biased coin tosses? Now you don't have a fair coin. You have an unfair coin, unbiased coin, sorry, biased coin. Now you want to simulate a fair coin. Can you do that? Okay. So now, so we are going from biased to unbiased. A coin C is heads. Probability of getting heads is, say, P, and probability of getting tails is 1 minus P, of course. And I want to get coin C prime. Probability of getting heads is half, and probability of getting tails is half. This is what I want. Harsh is saying, yeah, simply use two outcomes in this one. One, head tails outputs 1, and tail head outputs 0, and heads and tail should be rejected. Nice. Okay, good. Good. Others, any idea?
Sir, I assume that the probability, total probability should be 1. So if we will add the probability of heads and probability of tails and then divide it by 2 and then divide it by the total twice, then maybe like the numerator will get
Okay.
1. So yeah, basically this only. I just thought to make the probability anyhow 1 by 2. So that's what I thought.
Okay, okay. Yeah, yeah, that's not a bad attempt. Yes, yes, nice. So you mean something like this is corresponding to probability of either getting a heads
Yes,
or
sir.
tails.
So because P will get cancelled and ultimately it will be 1 by 2 only. So yeah, it's the same thing that if we toss the coin twice and if the first comes tails and the second is heads, we choose any one of them.
Yeah, sorry, repeat it again.
Yes, sir. Okay.
Yeah, sorry. Sorry,
Okay,
I
okay.
don't.
I just said that, if we first chose P and then 1 minus P, so it's basically first heads came and then tails came. So we can give this configuration ultimately to any one like heads or tails, and the other like tails and heads to the other one left. It's the same thing like what Harsh said. But my
Oh,
goal
okay,
was
okay,
to
okay.
convert the P and 1 by P into 1 by 2, so I thought it the other way.
Oh, okay, 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 okay. Good, good. So, okay, okay. So similar to what Harsh pushed.
Yes, sir.
Okay, okay, okay. Good. So, yeah. So what Harsh said is uh, simply use two outcomes in this one. This one HT outputs 1 and TH outputs 0 and HH tails should be rejected. Okay. Yes. So this is a very nice thing. This is a nice uh, uh, trick. It's very surprising also that you can get from a biased coin to unbiased coin. First of all. And this is called the von Neumann trick. If you've heard this name, then you might know that he was an important person in computer science. So it's that if you toss two coins, toss coin two times, okay, then what are the outcomes? The outcomes are heads heads, heads tails, tails heads, tails tails. Well, what is the probability of heads heads coming? Probability of heads is p times probability of the next heads is again p, which is p square. And what is the probability of tails tails coming? It's 1 minus p whole square, right? But I want half half finally, right? So what is the probability of me getting heads tails? It is 1 minus p, or p times 1 minus p. Oh, okay. And what about tail heads? It's the same thing. P times 1 minus p. 1 minus p times p, which is. So see here that both are half half. And here too, both are half half. And here both are p times 1 minus p, p times 1 minus p. So what are we talking about? We are saying that restricted to HT and TH, we are talking about a uniform distribution, right? So, but what about these two? We'll ignore them. So if, okay, if you get heads heads or tails tails, uh, repeat experiment. So this is like a failure, no? So you need to repeat your experiment. If you get heads tails, then output heads. If you get tail heads, then output tails, and you get a uniform probability. And um, right, so you can check the probability over the success, and then you can get um, uniform probability, and then it's not a problem at all. But the main question is the failures, right? This is the success. And you may need to repeat again and again. What if you never get head tails and tail heads, right? So is there a guarantee? Yeah, yes, Avisha, you saying something? Okay. Oh, okay, okay. No, I thought you unmuted. Okay. So what is the guarantee that this process even stops? No? So you need to additionally compute the expectation, the expected number of trials for first success. You need to show that this converges, and this value is gets larger and larger as the probability p gets more further and further away from half. So the further it is from the uniform distribution, from a unbiased coin, the more time it takes. The more number of times you'll probably need to toss your coin. Okay, so this you can try yourself. Yeah, but I gave you the general idea. Okay, is that fine? Well,
So to compute the first trials for success, we will also be needing the total number of trials allowed. Like, or we can do any number of trials.
So yeah, I'm saying you can do any number of trials, but at least you should guarantee that the trials
Okay.
ends.
So, sir, we
Right?
will be multiplying it by the higher or probability, I think. Like, if one of the probabilities is 0.7, then we will be, and if the total number of allowed trials are t, so we'll be multiplying t by 0.7. So, in that case, t is mandatory for a question.
Oh, no, no. I mean, at least for this part, we are not insisting that you are only allowed these many
Okay.
tosses. Okay, at least this
Okay.
question. Okay. If you say I'm only allowing these many tosses, then there is a limit to the kind of p probability that you have. Because, like I said, if your p is like either very small or very big, okay, very close to 1 or very close to 0, then you need more and more tosses. Okay, you so that you'll see when you compute this expectation value.
Okay.
Okay, so that's why I'm saying, so if you fix a t, the maximum number of trials, then you will be fixing p also, which means that you'll see that there are unbiased points for which you cannot do in less than some t many trials. Okay, so but for this question we are not fixing, but we at least want a guarantee that this process will end. It won't go infinitely.
Okay, sir.
Okay. Okay, good. So could you repeat that last part you said, please? Okay, Harsh. But I think you got the algorithm right. If you get a heads or tails, then you'll repeat the experiment. And if you get a head tails and output heads, tails heads, and output tails. Okay. Now, um, yeah. Oh yeah. Okay. So, but you need to. So this happens. So you'll output a heads or tails only if your round was successful. No? If your round that is you got a head tails or tails head. No. What if you had got a heads head or tails tails? You would have repeated it. The question is, okay, fine, you can simulate a unbiased coin with this algorithm, but you need to toss it more and more times. No, so let's say you toss it first time, you get headed. Let's say then you toss it again. Okay, that means you failed. You toss it again, you get tails tails. Then you toss it again, you get tails tails again. Then you toss it, you get heads, and so on. You should make sure that this process should not stop. No, the process should not go forever. No, this process should eventually stop. And you can even do better approximation by saying that okay, you'll need around these many experiments. You'll at these many trials. So this is what this expectation will tell you. The expectation of trials for success. So this is what I'm letting you guys compute for now. We can do it next week, but I want to leave a homework exercise also. Okay, expected number of trials. Try using some random variables. Okay. So yeah. Okay. Good. All good, no? Harsh? Okay. Good. Good. Um. Okay. Okay. Good. Oh, Kishore is not here. I just noticed. Okay. So now we come to this week's content, which is the probabilistic method. Okay. So now we come to this week's content. It's called the probabilistic method. This is a very, very powerful method. Okay, this is a very, very powerful method, and probability is all about um, uncertainty, right? It's about chances and stuff like that. Can probability even be concrete? Okay, can it be explicit? So that is what probabilistic method actually does. Probabilist is a way of guaranteeing existence of objects. Okay, you're guaranteeing existence of objects by using probability. Okay, so how do I do that? How do I guarantee the existence of objects using probability? Well, the core idea is that probability that an object exists, okay, is greater than 0. Okay, object exists in some set S, let's say. This means that the object exists in S. It's a very strange statement, you may think at first. Like, I mean, even if you understand it, then why is it even useful, right? It's obvious, you might say. But it's actually a very, very powerful tool. Or you can also say that expectation, okay, on say the number of occurrences of some um, occurrences of something, let's say A, in some scenario S, okay, is greater than 0, okay, is equal to A, let's say, is equal to some value E, okay, which is greater than 0. Then what does it mean? Then there exists an occurrence. Not only does there exist an occurrence of A, um, the number of occurrences, okay, a stronger statement is number of occurrences of A um, is at least the expectation. Okay, this statement requires a proof. I mean, it may be immediately understandable also why this may be true. Okay, for example, if the average run rate is say 10, then it makes sense that there is an over where the batsman has scored at least 10 runs. That is the entire reason that the average run rate was 10. So um, so it makes sense intuitively also, but this is a way to guarantee it. No? Yes, Ashwini, this recording will be available. Okay, you will be getting the link uh, over the mail. Also, there should be a Google Sheet where you should get it. But in case you want it, I can share it to you right now in the Google chat also. I mean, at the end of the class in the Google chat also. Just let me know. Okay. So, yeah, where was I? Okay, sure, no problem. Just remind me at the end. Okay. I have a very bad memory. Okay. Um. Yeah. Where was I? Yeah. I mean, for example. Yeah. And I'll cut this to the other page. Okay. So this is the probabilistic method. Now, I mean, it will be more clear when we demonstrate it with an example. Okay, here's the question. Let A1 to A1, A2, and so on, A and B. Sir, link please. Okay, okay, okay. I'll give you the link in case you are. Uh, just 1 minute. Okay, I'll give you my channel link. Okay, you can locate it from there. There is a playlist called Probability for Computer Science. You can check it out there. Okay, good. Okay, I've shared the link. Okay, good. So here's a question. Let A1 to A and be real numbers in 0, 1, between 0 and 1. Assume n is even. Show that S a subset. Okay, there exists a subset. Now I'm not talking about randomness. I'm not talking about a probability. I'm talking about strong guarantees. So show that you guarantee a subset exists of size exactly n by 2, such that summation, the sum of all those numbers is at least half of the sum AI. Okay, that is a subset of size exactly n by 2. You may think of doing this without the probabilistic method also. You are free to share those ideas if you want. Okay, for example, like let me say the real numbers between 0 and 1 are 0 0.5, 0 0.1, 0 0.3, 0 0.02, and that's it. Okay, so n equals 4 in this case. So and this is A1, A2, A3, A4. So there exists a subset of size exactly n by 2, which means subset of size 2. Okay, and okay, let's do summation AI first. Summation AI I equals 1 to n. So half of summation AI I equals 1 to n is what? 0.5, 0.3, 0.02, 0.1. So that will be 0.4 to 0.92. Okay, and half of that, which is something like 46.46. Okay, and suppose I take s equals 0.5 and 0.3. Oh, not s equals 0.5. These are labels. So s equals 1 and 3. Summation over I in s ai equals a1 plus a3, which is 0.5 plus 0.3, which is equal to 0.8. Okay, so clearly, therefore, summation ai ins. Okay, by the way, size of s should be n by 2, right? Which is 2. So therefore, I took 1 3. Okay, ai is at least 1 by 2. Summation I equals 1 2 and ai. I'll come to the probabilistic method of proving this, but can you think of an alternate way to
So
prove this?
arrange these values in the decreasing order, and then make a
Okay.
balanced partition. And that partition would be having half of the elements, and then definitely the sum of the elements in that partition would be greater than the remaining half.
Yes, if that is why is that always true?
Because I have arranged these values in the decreasing order. So, and then I
Okay.
pick the first half values. So clearly those values would be greater
Yeah.
than this half of the entire thing.
Yeah. Why should it be the
That would be
case?
the case because the first two values, the sum of the first two values would always be greater than the sum of the last two values, isn't it? The sum of the first n by 2 number of the values would be greater than the sum of the remaining n by 2 number of the values if the values have been sorted in the reverse order, say in the decreasing order. That makes sense?
Mhm. Because yeah, right. Now, because if it were not the case, um, um, if it were not the case, and the sum of the smaller terms is actually larger than the bigger terms, then it means that your sequence is not non-decreasing,
Yes, yes,
right?
yes.
Yes, right. Good, good. So what Goel is saying is simply what you do is like this is a constructive proof. Okay, this is a constructive proof. It's yeah. Thanks, Goel. Um, so the idea is that you do it in decreasing order. Okay, 0.5 and 0.3 and 0.1 and 0.02 decreasing or yeah, I found just not to confuse. Okay, decreasing order or non-increasing order, whatever you prefer. Decreasing order, and you are guaranteed that n is even anyway. Okay, now Coel is saying make a balanced partition. Okay, and name the first partition P1, name the second partition P2. Set the first partition to be P1, and he says therefore it is true that if I sum every element in the first partition, it will always be greater than half of the sum of the entire thing, right? Because if it were not the case, okay, if not, so s equals p1. So if not, so summation ai is less than, so this is true. If it were not true, half of summation I equals 1 to n, right? And this is I in s, right? And I can split this. Okay, I want to make this more rigorous, that's why, but let's see if I can do it or not. ai I in s, summation ai, I is not in s, right? And this guy and this guy are same. So let me subtract it. So therefore you have half AI summation. Yeah, this will work. This will work. So let me shift this a bit. Okay. Now, so this half will multiply inside, and then I'll move this entire thing to the left. Therefore, I get half of summation I in S AI is less than half of summation AI I is not in S. And this half will cancel out, right? And therefore, I have the summation of P2, okay, not in S means what? P2, right? So this is nothing but summation AI I in P2, right? Because not in S, and this was a complete partition. Okay, if it is not in S, then it is in P2, but because S is P1, right? And you have that the elements, the sum of the elements in P2 is larger than the sum of elements in P1. This would imply that this can only be true if there exists an element A in Pi, P2, such that A is greater than all elements for all B in P1. But this is not true, no? This is a contradiction. This is a contradiction because our elements are in decreasing order. It cannot be that there exists an element in P2 which is greater than an element in P1. Greater than all the elements in P1, in fact. So this is clearly, and therefore, because of this contradiction, this if not condition is actually, removed, neglected. Okay. So this is what you meant, no? Go ahead.
Yes, yes.
Okay, good. So is this clear? This gives you an explicit construction. Everyone, Shovan, Avisha, Renuka,
Yes, yes.
Ankita, Lawrence. Yeah. Okay. Harshul, this is clear.
If
I did not think of such a fantastic proof.
So,
I mean, this is a proof you thought about, Goel, but
yeah, so this, if not condition, I did not think of this, that if not, like, how to prove this thing. At the most, I could
yes.
think of in terms of, I mean, using the common sense that this can never happen, but yeah, this proof is good.
Okay, yeah. So this is just a rigorous form of the right one. Good. Okay.
sir, this
Yeah.
this
Harshul.
proof you wrote is true if not that if not part.
So this is my claim. Okay. This is my claim that it is true. I say, why is it true now? Because this is a proof by contradiction. Proof by contradiction is, here's my claim, this is true. I say, because if it were not true, then I'll get some weird, absurd things, which is, I'll get a contradiction. So it must have been that this is true. Okay. So in this case, for example, summation AI over S is always greater than half of the entire sum. This is my claim. I say this is true. Why is this true? Because I assume that, okay, if it's not true, okay, if it was not the case, that is, summation AI is less than half instead of greater than equal to half. Then after simplifying, I realized that, oh, it means that there exists an element in P2 which is greater than all the elements in P1, which is wrong, right? Because we assumed that it was in decreasing order. So it must be that the assumption that we made, if not, right? The assumption that we made, which was this, okay, that AI is less than half, was clearly false. So that is how you do a proof by contradiction. Okay, is that fine, Arshul?
The last line, half of sigma AI I belongs to S less than half of sigma AI doesn't belong to S. Okay, that came from the previous part.
Yes.
And this is sigma AI belongs to P2. And you wrote something in the box over there. It was
Yes,
not
yes.
visible.
This is the implication from here. Okay. Yeah, I have this bad habit of writing everywhere anyway. So the flow is that, okay, I get this. From here, I get the fact that sigma AI P2 is greater than sigma AI I over S. But S is nothing but P1. Okay. This is greater than this. And if
Uh,
this is greater than this, it must, oh, the only possibility is, and they are of the same size, the only possibility is because there is an element here which is greater than every element here.
wait. The last one. There's an element here which is greater than every element. I did not get this part. Did we mention it as somewhere that P1 and P2 are of equal?
This is true because P1 and P2 are if equal sizes.
Okay.
Okay, because otherwise you can further prove by contradiction here. You will just keep going down the rabbit hole. You can further
Oh,
prove by contradiction that, okay, if not, okay, and then obtain a contradiction again. But you can try it yourself. I mean, intuitively, it should make sense that if you have um, A plus B is greater than C plus D, equal number of elements, two elements on both sides, right? It must be that there is an element which is greater than both C and D. Because as soon as you put, let's say this is 0.3, okay, something plus 0.3 is greater than C plus D. Now C plus D could be anything, right? So C plus D could be zero point 0.7 plus 0.4. So this total gives 0.11. So what should the value of A be so that this is always satisfied?
0.8.
0.8. No, not even 0.8. Oh, wait. Yeah, strictly greater than. Strictly greater than. Not greater than equal. So 0.9,
Okay. Okay.
right? So you'll get 0.12 that way. So observe that 0.9 is greater than both 0.7 and 0.4. It cannot be that I'll sum up. Now, it cannot be that 0.9 is smaller than 0.7 and 0.4. It cannot be so. Otherwise, you'll get a problem. For example, like assume that this is, uh, you can assume very small values also. Okay, zero point 0.5 and 0.1, right? And A is smaller than both of them. So 0.2. Does this match? No, the inequality is wrong. Because this is 5, this is 0.6. Right? You can look at this intuitively on experimentation, or you can try to prove this. You can say, if not, let's suppose that there does exist an element, then you can further come up with contradiction. I can do that, but I think it will be a nice exercise.
All right. Sir, there was also one of the problems in assignment, I think. So we can also prove that there exists a subset of size exactly n by 2 such that sigma ai is less than equal to half of sigma ai. Both ways it would work, I think. Not just greater than equal to.
Yeah. That also you can summation AI INS is exactly equal to
Less than
is less than
equal.
equal to half of summation AI. This?
Yes.
Um, yeah, yeah. So how do you do this? Any idea? Using this Goel's proof, constructive proof. What change would you bring?
Sir, in the ascending order.
Yes. Good, good, very good. Instead of decreasing order, I'll do increasing order. And then choose P1 as my first half. Or I can keep it as decreasing order and choose S equals P2 instead of S equals P1. Right? And that'll do the trick. Good. So, yeah. So, yeah, to answer Harshul, yeah, this is also doable by that. But remember, this is not what I want to teach. Okay, this is not. This is just one way to prove it. What I want to teach is the probabilistic method. Okay. So here's the probabilistic method. Okay. Um. Okay. Let's see. Okay. A1, A2, and so on are real numbers, and oh, okay, they are not just real numbers. They belong to 0, 1, and n is even. Okay, and show that there exists a subset 0. There exists a subset 1, 2, and so on till n of size s equals exactly n by 2, such that summation ai I in s is at least half summation I equals 1 to n ai. Okay, this is what you want to show, right? Um, so this is what you want to show, okay, via the probabilistic. So now here is a way how to do it. Okay, proof. I will show you the proof without showing you the set. Okay, how do you do it? Proof is um, huh. So the proof is choose set elements of at random. Okay, what I mean by that is for every um, a in, I won't write a, let me write something else. For every okay, alpha in 0, 1 to n. Okay, a alpha is placed in S with probability half, and it is not placed with probability half. Okay, this is how I'll build my set S. I'll give a random set. Okay, so this is how you build a random set, right? Now let's make a random variable. Okay, let's say x is the total sum of elements in that random set S. So this is nothing but summation ai I in S. Not sum of elements in S, sum of elements indexed by S. Because the sum is not inside S, indexed by S. Right? vice test. Now what I'll do is I'll write it. Remember, like we've done so many random variables. No, I want to write summation x is equal to summation xi. I want it in the form x equals summation xi form. So here is one way to do it. Xi is ai if I is an s and 0 otherwise. But what is another way of saying I is an s? This means happens with probability half. So with probability half it is ai. But now notice that since x is the summation of ai over I in s, notice that um, x is nothing but summation xi I in s. Right? Because it is xi is equal to ai exactly. Even this is not I in s is also not required. I equals 1 to n. Why? Because this is exactly ai when I is in s and 0 otherwise. This is when I is not in s. Right? So this is true. This holds. Okay. So far so good. Now let's compute the expectation. Expectation of x is equal to summation over expectation of xi by linearity of expectation. I hope you guys remember. Okay. But right, and okay, where was this half term? Oh yeah, okay. Now xi, right? But and there are probabilities associated, no? With half probability it is ai, right? So expectation of xi is nothing but half. It is nothing but the probability itself. Remember, right? Because expectation is probability multiplied with the value itself, and for a binary variable, it is the probability itself, and the probability is ai. Oh, probability is half. Sorry, and with half probability, you get ai. AI times half. Right? And you collect all the half outside. And also, what did you have? You had that. What was x? What is x? X is this guy. So you expect that the summation of ai, I is in s for a random s, okay, is equal to half summation ai. And remember what I told you about expectation. This implies that there is an s such that the corresponding x, okay, the corresponding x, okay, is at least expectation. which is nothing but half of summation I equals 1 to n ai. So there you have it. You have the proof without actually locating that s. It's a very, very powerful method. You don't even need to see the set to actually conclude that there is such an s. Is that clear?
So I could not understand from this point. I could understand till deciding the random variable x.
Okay.
And that itself is a question mark, that how did we reach to this conclusion that okay, this should be the random variable. And then from that point onwards, the things are, I mean, if you can repeat that, would be fine here.
Okay. I'll quickly repeat that. But if it is not clear, I think if we do the next question, it will be clear. Okay. But I'll do it once anyway. Okay. So where were we? Okay. So x is the total sum. Okay, this is fine. Okay. So what we want to do is, why did we choose x as the total sum of elements indexed by s? Because we want a guarantee on the total sum. So a probabilistic method is to get guarantees. What do you want the guarantee on? The total sum on the elements indexed by s. So therefore, the random variable for which I would later take expectation is also the total sum of elements indexed by s. This is the entire reason that we chose this one. Okay. Now, and it is, yeah, because it is exactly this. Now, the question is, what do you expect this term to look like? What do you expect this LHS to look like? It turns out that the LHS, you expect this term to always look like this, look something like this. Okay, you can even give a, here we calculated the exact bound, but you could give a lower bound also, that's not a problem. Okay, now you give this, right? Now what does this mean? That since you expect the average, okay, the average over all s's is this, there should exist an s such that this sum is greater than this. This is a similar thing that we saw. Oh yeah, the run rate example I was giving, right? So let's say the expected run rate, okay, the average run rate is 10. Okay, this means there is an over. What is the average run rate? This is over the overs, no? Okay, so average run rate is nothing but expectation over the number of runs in over omega, and omega is an over, right? And the average, this is the average run.
Yes.
10 overs. So it cannot be that runs per over look like, say, 1 in the first over, 2 and 5, 7, 3, 1. It cannot be that all of them are less than 10. How can you suddenly get that the average is 10? It cannot be like that. There should be at least 1 over. There should be at least 1 over where batsman scored 10 runs. That is the entire reason that the average is coming to 10 somehow. Otherwise, it cannot be that everyone is concentrated below 10.
Sir, if only 1 over is bowled, then the run is exactly 10. If there is more than 1 over, then we can say there will be at least 1 over where the number of runs will be greater than 10.
Oh, yeah, sorry, scored is at least 10. Yeah, not equal to 10. Yes, that's right, Rohan.
Yes, I got it.
Okay, is at least 10. Okay. You can say something stronger also. You can say you can even say there should be at least one over where the batsman has scored at most 10 runs also. That is the reason why but it cannot be that all the overs are greater than 10. The same argument. Okay, good. Similarly, we are saying the average sum, the average runs, okay, is coming to like this half of summation AI. It must be that there is an S because you are taking the average over S. No, it means that there must be an S for which the expectation. Oh, okay, very sorry, very sorry. This should be at least. Yeah, the X. Oh, what did I do? Huh. This should be at least one S such that X is at least mm, huh, X is at least half of. Okay. Yeah, Harsh. Okay. But is this clear? Well.
Yes, yes, yes.
Okay, good. Okay, then we'll quickly move on to another question. I'll just take 5 minutes of your time. Okay? It's already 8. Yeah, I wanted to do this probabilistic method in detail, but you watch the lectures also, please, because there it's done in detail. All these Ramsey numbers. Ramsey numbers, I think, is the first um, uh, first problem where probabilistic method was used. It is introduced by Erdos. So if you know, Erdos was a great number theorist, great mathematician, combinatorist, who proved lots and lots of theorems. He traveled across the world and collaborated with mathematicians all over the world. Um, and this method is credited to him. And people, after seeing this, they applied it left and right. And it's used all over computer science also. Okay.
There is something called Erdos number as well, similar to the H index.
Oh yes. Erdos number is the collaborative distance you have from Erdos. So Erdos himself has a Erdos number of 0. If someone has collaborated with Erdos, for example, there is this famous Erdos-Zechariah theorem. So Erdos has collaborated with Zechariah, so Zechariah has a collaborator number of 1. And say Alan has collaborated with Zechariah, so he has a collaborator number of 2. And say Church has collaborated with Alan, so he has a collaboration number of 3. And similarly, Turing would be 4 and so on. Right? Yeah. There is a Bacon number concept also. There's an actor, Hollywood actor called Kevin Bacon. I think it's called 7 Steps to Kevin Bacon. The conjecture is that every person in the world is every person so in the world knows a person. Okay, so it's like every person is 7 steps away from knowing Kevin Bacon. For example, I know Kevin Bacon and you guys know me. So therefore, uh, is that how it works? Is it knowing? I think knowing personally, I'm not sure. But that there is
Yes,
another.
I also heard this theory that
Oh, you did. Oh, okay,
yeah,
yeah. Kevin Bacon now. But is it knowing them or is it friendship or something like that? I don't
I
know.
think it was finding them, something like that. I was also not
Okay.
sure.
Oh, okay. Sure. Okay. So now I'll just show you this question. Okay, let's see if we get to do it or not. But I'll try to dig your brains. Okay, with this question. another question on probabilistic method. Okay, so hashing we won't get to do. Okay, so prove that any graph has a bipartite subgraph containing at least half the total number of edges. Now this is a very strong statement. To come up with a constructive proof of this, it would be difficult, right? If you can attempt it if you want, but what it's saying is sorry. So for example, if my graph is this, okay. So the total number of edges is 1, 2, 3, 4, 5, 6, 6 edges. So I can always find a bipartite graph which has 3 edges here. So yeah, can you come up with a bipartite graph which has 3 edges here?
So, like, 1 is connected to 3. Need to convert this into the bipartite? Yes. 1 is connected to 3. They should not be, I mean, I should be able to segregate these, I mean, the vertices into the two sets in such a way. That's one of the things. So,
it is a bipartite subgraph, by the way. So,
oh, I see. Yeah. So that would be, then I can go for, let us pick one in the at the one end and then 3 at the other end, and there is an edge from 1 to 3. And then I pick say 4 in along with 1, and then 4 is also having 3. There is no issue with mapping, I mean, multiple number of the vertices, the second. And moreover, 5 can also come here.
Yeah.
And then 6 can appear along with 1, and then 5 towards the next side.
Yes. But I can't add 2 because this is an odd side.
Yes.
So that will make it non-bipartite. No? Okay, very good. Yes. So how many edges does it have? 1, 2, 3, 4. It has even more. At least half it's saying, but we have at least more than, so strictly more than 4 edges bipartite. And you can always find this. Now, this is a very, very interesting peculiar theorem. No? I will just give you this right away, that if you have a graph G over VE and size of E is M, okay, what I want, so I'll do the first half of the process, okay. That is, what I'll do is, I want to make a bipartite subgraph. I'll do it randomly. How will I do it? I'll divide V into A and B. And A and B are disjoint because, of course, they need to be bipartite, right? So vertex at A and vertex at B. And what I'll do is, I'll put a vertex V in V. Okay. For every vertex V in V, put V in A with probability half. I hope you can see the similarity with the previous question. And else put V in B. So I look at a vertex, I put it in A, okay, with probability half. And otherwise, let's say I toss a coin, let's say I get a tails, then I'll put it in B. And I keep doing this, right? Now, can you tell me, recall that we are trying to take expectation at the end, okay? So we need a random variable. What should be the random variable at the end? What should X be? Oh, okay, and once we do this, we'll be over.
So the random variable would be the count of the vertices in the set A.
count of vertices in the
Because
set
I
space.
mean, yeah, because then the depending upon this will reflect into the number of the edges.
But why would I be interested in the set A only? Like, I mean, A and B together form the bipartite graph, no?
Yeah, so for that sense, yeah, and with the also with the
But you
so
are
the
going.
so x would be the number of the edges from the set A to the set B.
Yes. Good. Yeah, Harsh. So Harsh, like I said, the random variable should always be estimating the final object count of the object that you are seeing. For example, we are bipartite subgraph containing at least half of the total number of edges. Okay, so it should be over the total number of edges intuitively. So x is the total number of edges, okay, from A to B, between A and B, right? Now I can break up x. Now I like before I want to write x as summation of smaller x's. But now I'll spoil it right away because we don't have time. I'll write x for each edge, xe, where e is uv, the edge uv, okay, and xe is 1 if u is in a, v is in b, or u is in b, v is in a, 0 otherwise. This makes sense, no?
So, but then I observed this much similarity in the previous solution and this one. In both the cases, you used
Yes.
indicative random variable.
No. In the previous one, I used a, what is it called? Bernoulli random variable, but not indicator, depending on what I want. Here it's AI, not 1. Now,
Oh yes,
right?
yeah.
So depending on what kind of weights I need, I was doing it. But this time I'm using indicator because it's simplified now, right? Because this is exactly 1, right? It is exactly 1 when there is an edge from A to B or B to A. I did not get the logic of U and V. Please explain. Yes. So, um, I'll yeah. Harsh, if you recall the previous lectures or previous problem solving sessions, what did we use indicator random variable for as a contribution to the sum? So x is the total number of edges. I want every edge that participates from A to B or B to A, okay, or B to A, okay, or I mean between A and B, okay, every edge to contribute to the sum. And indicator, it will contribute exactly 1, okay, if that edge exists, okay, that edge clearly exists, and it cannot be that u and v both are in the same partition. So what this says is that u and v are in different partitions. Yeah, this probably I should have mentioned, because if they are in the same partition, then the subgraph we finally come up with is not bipartite, no? Right? So it exactly counts those edges, okay, counts those edges. This xe gives a count 1, contributes 1 to this sum exactly when, okay, e and e, okay, exactly when u and v come from different partitions. If they come from the same partition, then it's not bipartite. Okay, okay, is this clear, Harsh? Okay, good. Now all we are left with is finding the this finding the expected value. Okay, so can you tell me what the next step will be?
So since we are using the indicator random variable here, so expected value is equal to the sum of the probabilities.
Sum of probabilities, correct? And furthermore, we can even use linearity of expectation to get this, right? That's how we reach to the sum, right? Now we can use the sum, right? Sorry, now we can use the probabilities, right?
Yes.
Now, since indicator is for indicator, expectation is probability, so which is sum over probability x is 1. But what is sum over probability x is 1? It is nothing but sum over probability that u in A, v in B, or is nothing but plus probability that u in B, v in A, right? Right? Now the final step. Right? Okay. Right? Now what are these probabilities? What is the probability that u is in A? How did we include u in A?
So
With what
included
probability?
with the half probability.
Yes, with half probability. And does the probability of being u in A affect probability of being v being in B? No. Right? They are independently done. Right? So these are independent probabilities, so you can multiply them. Which is equal to summation E in E half times half plus half times half, which is equal to summation E in E 1 by 4 plus 1 by 4 half. But what do we have? You have that E is nothing but m, and you are just summing up a constant over and over again. So we have this is equal to summation m times 1 by 2, which is m by 2. This is the expectation. But what was x? X was the number of edges in the bipartite. So expectation of the number of edges is at least half the total number of edges. Means, what does it mean? Means that there is a choice of bipartite graph. Right? Because the randomization was taken over A and B. Choice of A and B. There is a choice of A and B here, partitions A and B, which will actually have at least m by 2 edges between them. Okay, this means there exists A and B such that the graph over AB, okay, has at least m by 2 edges. And you see, we didn't have to find the right. Yeah, I hope you can appreciate this method. It's a beautiful method. Is there a recipe for applying probabilistic method to guarantee something? Yes. So this is the method, no? Well, to apply the probabilistic method, you need to guarantee an object or a count of an object. Okay, stepwise, yes. So that's what I was saying. So that's what I mentioned earlier. So, so to guarantee that an object exists, okay, you define a suitable random variable and prove that the probability is greater than 0. This is the general framework, okay. But for counts, it's a better idea that you can play with it more. If you want to guarantee number of occurrences of something, then you find the expectation. So if you're talking about existence, then use probability, and if you're talking about the count, then use expectation. Okay, but the inner workings is, I mean, of course, if it were that mechanical, then I mean, theorem proving would not be difficult. So there the inherent creativity again lies in, let's say, the choice of random variables and the intricacies of the methods you use inside and so on. But I hope you can see the power of this model, right?
Yes, yes, yes.
Okay. Good, then we'll break. Okay, it's been, sorry for keeping you so late. Hashing we could not cover. We'll let's see if I get the time, then we'll cover next week. So the final lecture will be final class will be next week. Okay.
Sure. Thank you so very much.
Yeah. Okay. Thank you.
Bye.
Good night.
Bye.
Yeah. Yeah.
Thank you, sir.
Okay. Thank you. Thank you,
Could you
Shovan.
show the last slide once?
Which slide, Harshul?
There exists A and B such that graph of A comma B that
Yes.
as greater than or equal to n by 2 inches.
Right? Because,
Yes.
yeah. Right? Because expectation is okay. So this is like your average run rate. So this is like there is an over where there are at least m by 2 many runs. Huh?
That's it, sir. Thank you.
Yeah. Thank you, Arshul. Okay. Good night. Okay, I'm stopping the presentation. Okay. Renuka Devi, is there any question? Should I end this? Okay, then I'll end the call. Okay. Okay.